This is the final stage of the SAR ADC inspired by Dr. Yamada. It will accept an analog input from 0 to 5 volts, like I'm doing right now, and then output a 7-bit binary representation of the input. The output is then displayed on the bar graph shown on the bottom right. The circuit is mostly functional with the exception of 3 bits always being on. The SAR is currently in free running mode, but by pressing the button it will switch to manual mode. Here's how the circuit works. So this is the schematic of the entire circuit. We can see the clock signal from the first project, which generates a wave which has a period of 103 microseconds. And we also see the sample and hold chip, which takes a sample of the analog signal from 0 to 5 volts and holds it for the SAR conversion process, and then compares it with the R2R ladder DAC output voltage. And the new components are the D flip-flops, the AND gates, and the shift registers. There's one shift register to test each bit during the SAR conversion process. And the second shift register is to show the full 7-bit digital approximation of the analog input. And we also have a switch to control the mode of the SAR ADC. It can be in either manual, which is controlled by a button, or in auto mode. So, in order for a bit in the SAR ADC to become high, the non-inverting input, or the reference voltage, which is the analog input from 0 to 5 volts, must be greater than the non-inverting input, or the input from the R2R ladder DAC, so that the comparator is high. Otherwise, the comparator will be low if the reference voltage is less than the R2R ladder DAC. So when the SAR ADC is initialized, the outputs of all the AND gates are 0 except the first one, since the input is wired to plus 5 volts, so it is always high. And so the output of the first AND gate is a 1. To understand the circuit a bit better, let's assume a sample voltage of 1.74 volts. So, on the first AND gate, the output of 1 will correspond to 2.5 volts on the R2R ladder DAC. Then this output will go on the comparator and be checked if the 2.5 volts is greater than 1.74 volts. Since the R2R ladder DAC's output voltage is greater than 1.74 volts, the comparator will output a low, which means the output to the AND gate will switch from a 1 to a 0, and so on the corresponding SAR AC output on D6, the LED will be low. So on the subsequent clock cycle, Q0, which is flag number 1, becomes high, and so the output on the second AND gate now becomes a 1. This corresponds to a voltage level of around 1.25 volts on the R2R ladder DAC, which is indeed below the 1.74 voltage reference threshold, which means that the comparator will become high, meaning that Q0 will stay high. And so the output of this AND gate is 1. And this process is basically repeated for each bit of the SAR ADC, basically comparing its output on the R2R ladder DAC with the reference voltage, and outputting that on the comparator, and this leads to 7-bit output. Here's a table showing the entire SAR output for the analog input of 1.74 volts, and you can see the calculations done on the DAC output column. The 0.03937 volts calculation, it was found by finding the resolution of the SAR ADC, which is 127, and this is divided by 5 volts, which gives us 0.0397.